This is AB Calculus Section 3.1, day number 1. Work with inverse, exponential, and logarithmic functions. Objectives, properties of exponential equations, rational exponents, and inverse functions. Some exponent rules for any base b, which is greater than 0, and real numbers x and y, the following are true. So rules of exponents. B to the x times b to the y ends up being b to the x plus y. B to the x divided by b to the y can be written as b to the x minus y. B to the negative y is the same as 1 over b to the y. And b to the x to the y power is our product rule of exponents, b to the x times y. When dealing with rational exponents, we have a power and we have a root. X is the power, and y is a root. So for example, if I have b to the 7/3 power, that could be written as b to the 7th to the 1/3 power. Or it could also be written as the cube root of b to the 7th. So let's look at a couple of examples. 8 to the 2/3 power, a couple different ways you could rewrite this. That would be equivalent to 8 squared to the 1/3 power, or 8 to the 1/3 power squared. Okay, I'd prefer to work with the second form. So 8 to the 1/3, which is the cube root of 8 squared, is equivalent to 2 squared, which would be 4. 81 to the negative 3/4 power is equivalent to 81 to the 1/4 power, or the 4th root of 81 to the negative 3rd power. That's likely how I would work through it, because I know the 4th root of 81 is 3. So this would be the same as 3 to the negative 3rd power. And as we saw in the rules above, if b is taken to the negative y power, that's the same as 1 over b to the y, which would be the same as 1 over 3 to the 3rd, which would give us an answer of 1 over 27. Okay, so something interesting to think about is it possible to raise a positive number to a power and obtain a negative number? Well, as we recognize, let's say b equals 5, and I take 5 to a power, right? And that's going to give me some y value. The larger that x gets, the larger the actual value gets. So as we were to sketch this graph, b to the 0 or 5 to the 0 would be 1. And then as x gets larger, y gets larger. It's an exponential function, it's growing. But as x gets smaller, all that we're going to do, let's say that y is equal to 5 to the negative 100th. Well, that's still going to be positive. It's going to be 1 over 5 to the 100th, but it's going to be approaching 0. So as x approaches negative infinity, it approaches 0. Therefore, it's not possible to create a negative number by taking a positive number to a power. Is it possible to obtain 0 by raising b to a power? Also no. Right? You see that we're approaching this horizontal asymptote, never will equal 0, right? It'll get really, really close, but never get there. Okay, some properties of exponential functions. So if we let b be a number greater than 0, and f of x is equal to b to the x, the domain, we can plug any number in for x. So our domain is all real numbers, written either in that way or in this interval notation. Okay, the range though is from 0 to infinity. Right, we saw in our sketch above our function, our function here, its lower limit is 0, never equaling 0, and its upper limit doesn't have one. So the range is 0 to infinity, regardless of what b is. Now if b is greater than 1, this function is going to be increasing. So if b is greater than 1 and f of x equals b to the x, our function will look like this to some extent, in which, of course, all functions of the form f of x equals b to the x will go through the point 0, 1. If b is between 0 and 1, then it will be a decreasing exponential function, or an exponential decay function. So it will still go through 0, 1. It will just decrease instead of increasing as x increases. Okay, so now one thing you do want to be aware of is that you could be in a situation where b technically is in between 0 and 1. For example, you could have 4 to the negative x. Now, this technically you could look at and say, well, b is positive, but x is negative. Therefore, this is equivalent to 1/4 to the x. So you just want to be careful. This is a decay model. All right, just something to be aware of. Okay, let's look at some more with exponentials and logarithms. All right, inverses. The inverse function, given a function f, its inverse, if f exists, if it exists, is a function called f inverse of x, such that whenever y equals f of x, then f inverse of y equals x. Another way to interpret this, the inverse function undoes the original, or if we start with a value of x, apply f to it, then apply the inverse to f of x, the result is x. In simpler forms, the inverse of f of x, if I were to do a composition, equals x, and f of the inverse also equals x. So it's 2 steps in order to find an inverse. All right, so say I'm given a function and I want to find its inverse. First thing you do is you swap the x and the y. Okay, you swap the x and y, and then you solve for y. And when you solve for y, you have now gotten the inverse. You found whatever the inverse function is. Now, the interesting thing with domains and ranges, because we're switching x and y's, we're also switching domains and ranges. So the domain of f becomes the range of f inverse. Now, there are some cases where you need to be careful, but we'll talk about those as we go. The range of f becomes the domain of the inverse. So let's look at an example here. Find the inverse function of f of x equals negative 3x plus 4. Then prove that you found the inverse. Okay, so first I'll find the inverse. So I'm going to rewrite this as y equals negative 3x plus 4. And in step 1, I said switch x and y. So we're going to switch those. And then we're going to solve for y. So I'm going to subtract 4, divide by negative 3. So y equals x over, negative 3 plus 4/3. All right, so this is our inverse. And plus 4/3. Now I want to prove that f of x and f inverse of x are inverses. So what I want to show is that f of f inverse of x equals x and f inverse of f of x equals x. If both of those are true, we have shown and proven inverses. So f of f inverse of x, let's plug that in. So f of f inverse of x, I'm going to run out of space here, so I'm trying to squeeze this in here. That'll be 3 times what I found the inverse to be, negative x over 3 plus 4/3. So let's simplify. I'm going to distribute the negative 3. That gives me negative x, positive x minus 4 plus 4. Well, that comes out to be a positive x. So that side checks. Let's work the other side. So f inverse of f of x. F inverse is negative x over 3 plus 4/3. So I'm going to plug in f of x, negative 3x plus 4. So simplifying, it looks like I would get, let's see here, the negative would distribute, so I'd get a positive 3x over 3 minus 4/3 plus 4/3. It looks like I'm going to get what I want. Therefore, f of x equals negative 3x plus 4, and f inverse of x is equal to negative x over 3 plus 4/3 are inverses of each other. Great. Part B says graph f and f inverse. All right, so f I'm going to graph. We'll go up here to 4 with a slope of negative 3. There is f of x. And f inverse has a y-intercept of 4/3 and a slope of negative x over 3. Negative x over 3. So down 1 over 3. Okay, I think my sketch is not very good there. Let's see if I did something wrong. So negative 3. Oh, yeah. Yeah, we got issues. I think my issue is with f of x. So we would have had a slope going through that point. So there's an adjustment. That was my fault for f of x. But then here is what we would consider f inverse of x to be. And the reason I could kind of isolate that is because what you'll notice, and I'm going to answer the next couple of questions through this process, is that inverses are a perfect reflection about the line y equals x. So I'm answering part C. What line do these functions have symmetry over? Graph the line of symmetry. It's the line y equals x. So in this case, with lines, there's not going to be anything groundbreaking with parts D and E, but the domain and range of f is all reals. And it's not going to be all that pleasing here because it's, it is what it is, but the domain, or the range then of the inverse is going to be all reals, but you can't really see it unless I change the colors here to show you how these relate, right? So the domain of the inverse is equivalent to the range of the original, and the range of the inverse is equivalent to the domain of the original. So we're going to see a more complicated example here on the next slide where you'll see this take shape and possibly some restrictions on the domain. Okay, so up comes the question, like, when does an inverse function actually exist, right? So the function f has an inverse that also is a function when f is 1 to 1, or when every output of f has exactly one input. This is checked graphically by using what's called the horizontal line test. So for example, if I were to graph f of x here, 4 to the x. Okay, this function is 1 to 1 because if I were to sketch a horizontal line, it would pass, right? Pass meaning it would only cross the function once. That tells me that its inverse is also a function. However, if I were to graph g of x, so this is 1 to 1. If I were to graph g of x, this is a quadratic shifted left 3 units and up 1 unit, and I'm just doing a general sketch here. It's going to open upward. That would not pass the horizontal line test, right? So in this form, its inverse would not be a function. So what we need to do is we end up splitting it up such that it becomes two functions whose inverses are both functions. So that's the point of the horizontal line test and potentially restricting the domain. So which function is 1 to 1? We said f of x was 1 to 1. Which function is not? We said g of x is not 1 to 1. Restrict the domain of the function that is not 1 to 1 in order to make it 1 to 1. So if I restricted g of x, and I said that the domain of g of x was, and in this case, to maximize and get a function that that's domain, or excuse me, that passes the horizontal line test, I could do one of two things. I could either work the domain and say from negative infinity up to -3. Or I could work on the other side of the quadratic and say from -3 to infinity. Right? Either way, and so if I were to sketch that, this domain would be that portion of the graph, and this domain would represent this portion of the graph. So now the red portion would pass the horizontal line test, and so would the green portion if they were done individually. So let's look at an example of that and coming up with an inverse for a restricted domain. Okay, so it says to graph f. Okay, so -x cubed minus 3x, or excuse me, minus 3. So here's a graph of -x cubed minus 3. So this is the point 0, -3. This would be the point 1, -4. This would be the point -1, -4. Okay, so clearly this does not pass the horizontal line test, so the function is not 1-to-1. If we restrict the domain of the function, let's take this right side of the function. So the domain for, is it f? Yes, f of x in this case would be 0 to infinity, right? What would the range be for that part of the function? Well, the range would be from -infinity up to and including -3. Okay, so it now says find f inverse on both intervals. All right, so this is interesting in that, you know, we're just going to work with f of x and then adapt it to what we see here. Okay, so first of all, let's go ahead and write this f of x in y equals form. And then step 1, we said switch x and y. So then I'm going to solve in part 2 for y. So I'm going to add 3. And then I'm going to divide by a -1, so it's -x minus 3. And then I'm going to take the square root. Now when I take the square root, 2 stems of a square root show up, right? A positive and a negative. I'm going to factor out the x, okay, plus, or excuse me, -1. So if I were to graph, let's just say I were to graph the positive portion of this square root, right? So -x plus 3. Well, what would that look like? That would be a shift left 3 units of what function? Well, the square root function, right? So its parent function is the square root of x, which of course looks like, let's put it up here, looks like this. Okay, now I'm going to shift it left 3 units after a horizontal reflection. So I'm going to reflect it horizontally and then shift it left 3 units. So it's going to look like that. Now look at how that matches up nicely with the green portion of my quadratic. So that would be the inverse function. And as I'm looking at this, I think, okay, well, how about that reflection over the line y equals x? Is it a good reflection over that line? Yes. Look at the points. 0, -3 becomes -3, 0. We said change the x's and the y's. Perfect. 1, -4 becomes -4, 1. Outstanding. Okay, so I've found f inverse on that interval. So the domain here for this portion, the domain of f inverse of x on this section of the graph is -infinity up to and including -3. How does that pair with the range of the original? It works out perfectly. What about the range of the inverse on this portion? Now this is where it's going to differ slightly. Well, actually not at all. The range is going to be from 0 to infinity. Okay, awesome. All right, now let's look at the other stem. The other stem for f of x, if we were to restrict, would be from negative infinity to 0, and the range is going to be no different than the other. So it'll be negative infinity up to negative 3. So let's look at now y equals, or f inverse equals, negative square root of negative quantity x plus 3. Okay, so the domain of this, let's look at it graphically first, and the range of this should match that of these domains and ranges up here. So I'm going to flip the two. The domain from negative infinity to 0 is now the range of the inverse, and the range of the original should be the domain of the inverse. So let's see how it shows up here. Well, this is going to be the same sketch of the green graph, except it's reflected vertically. And there you have it. Okay, that matches those domains and ranges, and shows you the relationship between f and f inverse. It looks like I graphed f inverse, so I think we're good. That's it for today's video on inverses and some exponential work. See you in the next video.